Hello guys, welcome back to Foolish Engineers video. Today we are going to look at such an application where Opamp performs calculus operations like integration and differentiation. In this video, we'll see the basic concept of integrator and see how to design one. So let's start. While learning math in younger days, we have seen integration and derivation. Well, that was one of the boring phases in math. But that boring stuff can be done by this op-amp now. Well, not now, earlier only, but we are discussing now. As we know, integration is basically the area under the curve. That means when we provide a normal linear curve, its integration will be a ramp output increasing linearly because the area under this curve will add up. With the same logic, if we have a square wave, it will provide a triangular waveform at the output. The circuit of this integrator looks like this, with one resistor and a capacitor at least. Well, we need reactive components like capacitors to do mathematical operations like this. You'll find many videos where you'll get the derivation or math behind the circuit. And there are some actual good videos related to that. But in this video, we'll see how to design and integrate a circuit. Let's see the example. If you provide a square wave, the change in the input signal amplitude charges and discharges this feedback capacitor. So it gives a triangular waveform at the output. During the positive half cycle of the square wave input, a constant current flows to the input resistor. Let's assume this is an ideal op-amp and current flowing into the op-amp is 0. So all of the current flows to the feedback capacitor. This current charges the capacitor. As the capacitor is connected to the virtual ground, the voltage across the capacitor is the output voltage of the op-amp. During negative half cycle of the square wave input, the current is reversed. The capacitor is now linearly charged and produces a positive going ramp output. Let's say we provide a DC signal at the input. The feedback capacitor behaves like an open circuit. So there is no feedback from the output to the inverting input of the op-amp. Now the circuit behaves like an open loop inverting amplifier with very high gain. And we all know from our last video that because of the open loop amplifier, we get saturated output voltage. As the input frequency increases, the capacitor charges. At higher frequencies, the capacitor acts like a short circuit. To avoid the saturation of the output voltage and to provide gain control, a resistor with high value can be added in parallel with the feedback capacitor. In that case, when we get DC signal at the input, it will simply work as a normal inverting amplifier. This is the same circuit for active low pass filters. Don't worry, there will be different video for that. For now, let's focus on the integrator. This is the frequency response of the circuit. Basically, it shows how output will behave when there is a change in signal frequency. On the y-axis, there is the gain at the output, which decreases as the frequency increases. Well, this feedback resistor plays an important role here. At higher frequencies, it works as the integrator. And these are the formulas where we can distinguish these so-called higher frequencies. So the input frequency must be between these two. Well, we check the circuit of the op-amp. Now we'll see a design of such an op-amp based integrator. We'll assume that we are getting different type of signals at the input to get integrated, which have the frequency in the range of 100 Hz to 100 kHz and whose amplitude will be less than 2.4 volts. The 0 dB frequency is always 1 kHz, then decreasing, like this shown in the diagram. Now, this is how the circuit would look like. With an input resistor, there is a feedback capacitor and a feedback resistor in parallel. We'll connect VCC and VEE to this op-amp of around 2.5 volts. VCC is 2.5 volt and VEE will be minus 2.5 volts. There are a few important points that we need to consider while making this circuit. We should select a CMOS based op-amp to minimize the errors from the input bias current. The value of this feedback resistor should be very high. The gain bandwidth product of the circuit will set up the upper frequency. And an adjustable reference voltage should be connected to the non-inverting input of the op-amp to cancel out input offset voltage, or else the DC noise gain will saturate the circuit. Now let's calculate the required values of these passive components. Considering all, this would be the transfer function, or we can say the relationship between output and input voltage. We'll start with the input resistor. For now, we'll select the resistor value of 100K. Now we'll calculate the value of this feedback capacitor, which can be calculated with this formula. For this, we need 0 dB frequency, and it turns out to be 1.59 nanofarad. And finally, we'll calculate the value of this feedback resistor with this formula, which we get as 100 mega ohms. As we saw, the gain bandwidth product of the op-amp sets the upper frequency. So we have to select an op-amp which has gain bandwidth of at least 10 times the maximum operating frequency, which will be around 1 MHz. For that, we'll use TLV9002 op-amp IC. We can also simulate the circuit using Tina TI software. I've added the link of the simulation files in the description. Now your circuit is ready. Well, we use such type of integrator circuits in old analog computers, ramp generators, wave shaping circuits, and analog to digital converters. For example, this integrator circuit is used as a ramp generator or even a control circuit in the PID controller, which we need in the switching regulators or motor controllers. We saw such circuits in this CCCV charger video as well. Well, that's a wrap. I hope you picked up something useful from this video. The reference of this design is added in the description below. While checking the reference, please don't forget to hit that subscribe button as well. It's right over there. I'll see you next time. Till then, stay hungry, stay foolish,